Good afternoon, everyone, and also thanks to organizers for this opportunity to give this talk. So, extreme conditions and nuclear waste, how does it go together? So, I will start my talk with a very general introduction to the current problematic of storage of nuclear waste. And I show you some examples from our studies, in particular how we mobilized actinides in yttrium stabilized zirconia phases, and I will show you concomitant structural evolutions which we have found during this process. And in the second part of my talk, I will present you some recent temperature and pressure dependent studies on these systems, on the BIM20 Robel beamline. So very general nuclear waste, a general concept for long-term underground storage. It's you extract spent nuclear fuel from the nuclear reactor together with rods, and you put it underground. So you find a specific site with a geologically stable bedrock, and it should be deep. So there have been and are considered different depths for this kind of applications, depositories, starting from 500 meters up to even 15 kilometers. And this would correspond to pressure range of 0.01 to up to 0.4 GPa. But I must say that to the best of my knowledge, currently only 2 countries have made final decisions in this direction. What I mean by this, it's a choice of specific site and specifically also the procedure for this storage. But of course, you don't just simply take your spent nuclear fuel and deposit it into this underground. Usually it should be protected by multi-barrier systems, and typically these are originally, firstly you enclose your spent nuclear fuel into canisters, metal canisters, and then on the top you pour something like concrete, for example, it could be bentonite. So you seal this completely, all this storage, and for very long time. Very long time. Here I speak about even millions of years, because in spent nuclear fuel you can have some long-living radionuclides, like for example neptunium-237 with a half-lifetime of about 2 million years. So this kind of setup, depository should be stable. So that's why there are a lot of studies which are ongoing on the stability of this kind of confinement, especially with respect to the corrosion, and then studies on possible diffusion of radiotoxic elements out of this canister to the surrounding rock, and so studies on the rate and distance. So from our side, what we propose, we work on these solutions to immobilize these radiotoxic elements in host matrices on atomic level. So in this case, you would reduce or eliminate migration of these radiotoxic elements to the surroundings. So we wouldn't anymore be worried about this phenomenon of diffusion. And of course, it would result in a higher long-term safety of these kind of depositories. So if you have a candidate phase for these kind of applications, typically you study maximum possible intake of radiotoxic elements. In this case, I will speak about tetravalent actinides. Then you study structural stabilities of these phases, and at the end, radiation resistance and leaching resistance. And today I will present you one case. This is zirconia-based systems. Why zirconia-based systems? Because zirconia, it's geologically stable, even on the time scale of billions of years. And zirconia, it's simple formula, zirconium-02, but it has now 5 different structural polymorphs as a function of temperature and pressure. And so since we want stability, so we want to stabilize one specific modification. And usually you can stabilize one specific modification of zirconia by doping. And today we'll speak about doping with yttrium. And I will start with tetragonal stabilized zirconia. So it can be obtained with yttrium contained from around 5 to 15% when you quench from this high temperature region where the cubic phase exists. Okay, so synthesis in principle it was done in collaboration with my colleagues in Germany, in HZDR, Dresden, Institute of Resource Ecology. Synthesis was done with co-precipitation method. So we want to incorporate thorium in this matrix. What can we expect? Thorium, it's larger, thorium-4+ is larger than zirconium-4+. So we expect that the unit cell will be expanded, and this is indeed what we observe. Up to roughly 10 atomic percent of thorium, when you introduce it, unit volume expands, and then you have a precipitation of thorium oxide. So solubility limit for tetragonal phase set up to thorium is about 10 atomic percent. And also we would like to know what happens here at this region when you introduce thorium to the structure of the system. So initially, for this reason, we synthesize more samples with finer steps in this region, and then we performed high-resolution diffraction studies on the Robel beamline. On Robel beamline, we have 2 diffractometers, and this is XRD1 high-resolution powder diffractometer. So with this machine, you can get resolution of up to 10⁻⁴ delta D over D. And very recently, actually last weekend, we have commissioned a new detector with a IGR2 with smaller pixel size. And we further increase the resolution up to almost 10⁻⁵ delta D over D. And you can get excellent powder diffraction data and perform quality refinement of structure. And actually, in this tetragonal zirconia, you have only one parameter to refine. This is Z of oxygen atoms. And so when you introduce thorium into this system, as expected, you increase the volume, but also what we have found that upon thorium intake, the Z of oxygen atom systematically decreases. So what it would imply from a structural point of view, in a tetragonal zirconia, there are 2 sets of oxygen atoms. Actually, I mark them here, oxygen prime, oxygen double prime. So you have 2 sets of distances. And if you have this kind of increase in zirconium oxygen Z coordinate, by symmetry, you expect that zirconium oxygen prime distances would become longer. So these atoms would move farther away from the central zirconium atom. And these zirconium oxygen double prime distances, they would decrease. But what we observe that only these distances, zirconium oxygen prime, they increase, and it results in flattening of this zirconium polyhedra. So indeed, you see these blue distances, they increase, and these bonds, zirconium oxygen double prime, they are stabilized. And how does it happen? Actually, it's possible because of strongly anisotropic lattice response to incorporation of thorium. In fact, in a AB plane, lattice exhibits twice as faster expansion than in orthogonal C direction. And also, in addition, when you introduce thorium, you decrease the tetragonality of the system. So tetragonal distortion, you see C over A ratio is decreased. So there is a clear tendency towards a higher cubic symmetry. Of course, obvious to try to introduce thorium into cubic yttrium stabilized zirconia. This is what we did for yttrium stabilized zirconia for high yttrium content. And indeed, we found that cubic phases can incorporate 20% more of thorium. So what about structural stability of these phases under extreme condition of temperature and pressure? And for these studies, we have used cerium 4 ions. These ions are widely used as surrogates for tetravalent actinides. Firstly, because it makes everything simpler, because they are not dangerous and not radioactive. There is no limit on sample volume and no limit on what you can do. And we perform, so even I was able to perform the synthesis at ESRF in our chemistry laboratory of Robel beamline. And then we performed serious diffraction studies, function of temperature using hot gas blower, and the function of pressure using diamond angle cells. So why temperature? Imagine you have a failure in the underground storage. Could be fire, could be some tectonic instabilities over a long period of time. And why pressure? Because we are underground. Well, pressure for the high pressure community, it's quite low, from 0.01 GPa or maximum 0.4 GPa. But we apply this pressure for hundreds of thousands of years, even millions of years. And you cannot exclude it can be increased during this time due to some possible tectonic instabilities, explosions. And so we apply higher pressures to push these systems to extremes and to induce possible structural evolutions, transformations, which could occur over this long time of storage. So what is concerning temperature, all of the study samples, 10 in total, so 5 for tetragonal symmetry, 10 for cubic symmetry, they exhibit excellent structural stability, function of temperature up to maximum study temperature of 1150 Kelvin. You see here, you have this tetragonal splitting, and it remains here at even 1150 Kelvin, and even on cooling. It's quite remarkable because here you crossed twice this portion of phase diagram where you have formation of monoclinic phase. So really this phase is stable as a function of temperature. And also what is important, occupancy of cerium, these guest cerium atoms, which are surrogate atoms for tetravalent actinides, doesn't decrease with temperature. So it stays there. You see this is blue dots. So occupancy of cerium ions, it remains stable within the error range. And from this kind of data also we obtain important physical parameters, which are coefficients of thermal expansions. And we found that cubic cerium doped yttrium stabilized zirconia phases are slightly stiffer than the corresponding tetragonal compounds. Okay, so what comes to pressure, we used diamond angle cells kindly provided by ESRF high pressure laboratory for this experiment with cerium dome samples. So, and it was actually first high pressure experiment at Robel beamline. It was done last year. Here you see the setup. This is now XRD2 diffractometer, multi-purpose diffractometer. So here is a diamond angle cell mounted on uniaxial goniometer. And here we have a large Pilatus 2M photon counting detector. From technical point of view, Robel beamline, it was not designed for a microfocus beam, but thanks to the ESRF-EBS source, now we are able to focalize beam down to 1990 micrometers at 32 kiloton volts. Because it's still quite large for high pressure community, so we are limited in pressure, let's say up to 20 GPa. But because of this beam size, you see this is actual raw diffraction data. We have excellent averaging of powder rings, they are fully continuous. And you are able to reliably perform full structural refinements. This is one example with agreement factors on order of a few %. And I must say, we didn't observe any kind of parasitic signal, neither from gasket or pressure markers up to the highest studied pressures. So I will briefly show you two examples. So one example is the cubic yttrium stabilized cerium doped phase, and another one is a tetragonal phase. Well, cubic phase, up till the maximum studied pressure of 11 GPa, it remained stable. So it's quite boring of scientific point of view. Nothing happened at all, but it's good from the point of view of stability. Things were more interesting with tetragonal phase. In fact, we did observe a transition around 9 GPa from tetragonal to cubic modification. You see here this tetragonal doublets are merged, and you have formation of one single cubic peak. So when you have this tetragonal to cubic transitions and you remove this liberty of this Z oxygen coordinate, it should go to 0. And in the refinement, point by point refinement, indeed shows that this Z of oxygen decreases and then it falls to 0. So this is a transition of the second order of a displacive type. So it's quite nice, but the most important, what happens with these incorporated cerium atoms, which is surrogate, is a surrogate ions for tetravalent actinides. We're able to refine their also occupancies throughout the studied pressure range, and what we found that within the error range, occupancy of these guest cerium ions remain stable. And would like to say that these in situ high temperature, high pressure diffraction techniques at Robel are available for external users through standard ESRF proposal system. And if you have some ideas, you're welcome to contact us to discuss. So conclusion for scientific part, these experiments, they showed that excellent affinity of these cerium atoms with these yttrium stabilized zirconia systems. So these phases, yttrium stabilized zirconia phases, are promising candidates as host matrices for radiotoxic tetravalent elements like uranium, thorium, or plutonium for long-term and secure storage of radioactive waste. So next, we are planning on these systems to perform radiation studies, so to simulate influence of radiation during long term, and then we can conclude on their performance. And then next step is to perform in situ studies already on radioactive samples, and of course we have to take then all the safety precautions into account. And so this talk actually is presented in this section, Emerging Topics in High Pressure Science. And I must say, these kind of studies on temperature and pressure dependence on these kind of systems are not typical. And I think this kind of studies should become routine and be a part of a protocol to validate these kind of systems for these applications. So I would like to acknowledge collaborators, especially from Germany, from HDR, and also my colleagues from Robel and ESRF for the technical support, and BMBF for project support. And thank you for your attention.
Thank you, Vladimir, for this nice talk. So I think I will ask the first questions. So you're speaking of 5% of the radiotoxic element inside the zirconia matrix. Is it feasible for storage? Is it a viable way, or could you put more?
So these phases, they exhibit maximum solubility limit of 10%. But even you don't want to put more, because then your material will become too hot and unstable in nuclear point of view. So okay. This is why these are typical concentrations we are looking at.
Okay. So your funding agency are really considering this kind of material as a possible technological...
Yeah, so we are developing, we are characterizing them. And what is important, if we want to find the ways to make them attractive for nuclear industry. So to make this large-scale synthesis possible in a more straightforward way. So at the end, to make it cheaper. It's also one point to consider.
Okay, thank you. I don't think there are any other question. No other questions. So we have to move for the next talk. Thank you, Vladimir.
Yeah, thanks.
So Maxime Pikov. Okay, Maxime is going to speak about new opportunities for high pressure chemistry in diamond and cell at ESRF.
Thank you, Paul. Can you see my screen?
Yes, good.
All right, good afternoon, everyone. So today I will be speaking about the opportunities which synchrotrons and ESRF-EBS in particular provide for high pressure chemistry from the perspective of a synthetic chemist. So we know that pressure can influence physical and chemical properties of elements and lead to the formation of compounds which are unthinkable at ambient conditions. Among some of the highlights from the previous years, we can mention sodium halide, which is an electrolyte compound, sodium Cl3 synthesized by Zhang in 2013, and of course a series of polyhydrides which are considered as high pressure, high temperature superconductors, and which is a clear which clearly revolutionized the field of high pressure solid state physics and chemistry. So when I show you all these three examples, I demonstrate you the crystal structure, and that is because crystal structure is the key element to understand the formation of these compounds, to understand their chemistry and properties. And the main method to study the crystal structure is X-ray diffraction. And we can use X-ray diffraction in its different forms to study chemistry at high pressure conditions. Historically, we use powder X-ray diffraction to do that. And this works really very well when we have simple chemical reactions, formation of binary compounds, for example, with simple stoichiometries and standard structure types. And we always like to see the diffraction pattern like this, which is very clean without any additional products, as in this example of the synthesis of palladium N2. The diffraction pattern can be easily indexed with a cubic primitive unit cell, and one can perform real Rietveld refinement with the determination of atomic coordinates, not just the profile fitting, to solve and define the crystal structure. However, this simple case is actually quite rare in what we actually do at very high pressures. Sometimes we get something really very unexpected, and we get multiphase products. And in this case, a very powerful method is when we use the experimental powder X-ray diffraction plus evolutionary structure prediction algorithms, for example, which give us some candidate structures, and then we compare the powder patterns of these simulated structures with the experimental one, and choose the one which fits best, which fits better. This approach has resulted in many success stories and really allows to get novel structure types and stoichiometries. However, it's still limited to quite simple compounds, and it is common that in the high pressure synthesis we have really complex structures with more than 50 atoms in the unit cell and multiphase products. In this case, the analysis of such experimental powder diffraction patterns becomes very ambiguous and usually biased towards theory. So once you start throwing more and more phases to fit such a diffraction pattern, you of course get better residual values, but it doesn't mean that you get a correct result. In our studies, we usually use a single crystal X-ray diffraction approach. In a diamond tunnel cell, we would put several pieces of our reagent embedded in the pressure transmitting medium that can be used also as a reagent. And before laser heating, we see the nice powder pattern. So this is the powder pattern from iron embedded in nitrogen. And after laser heating, we see the formation of multiple very sharp single crystalline spots, which are quite well separated from each other. And if you find a way how to understand where these nice sharp spots belong to which grain, we will be able to determine the rotation matrix and then use very well-known approaches of single crystal X-ray diffraction to solve and refine the structure without prior knowledge about its structure type, composition, and possible candidate structures. In a typical experiment, we would rotate a diamond anvil cell around one of the ganimeter axis in a range of plus minus 38 degrees and collect diffraction pattern every 0.5 degrees. This allows us to reconstruct the peak search table in 3D, and then an experimenter would manually select the lattice of usually one of the strongest diffracting grains from this cloud of peaks. And actually, when we started this, doing this kind of chemistry, this was the most difficult part to enter this field, because it really depends on the patience and the qualifications of the experimenter. And now the younger generation of PG students from Leonid Dubrovinsky seems to solve this problem. And for that, you should stay tuned for the next talk by Andreas Landukov at just after my talk. So once we have the determined lattice, we can integrate the data and solve our structure. My research is mostly concentrated on the studies of nitrogen chemistry at extreme conditions, and we know that pressure really unlocks the structural diversity of nitrogen itself, which forms numerous molecular phases below 1 megabar, and then it polymerizes to form CGN and BPN polymorphs. And these materials are considered as very high energy density materials because a huge amount of energy is released when these compounds are transformed back to very stable nitrogen molecule. So due to the very high polymerization pressure, these compounds are not really useful for their applications in as high energy density materials. However, if we add additional element, usually electropositive metal, we can stabilize various polymeric nitrogen species, starting from really small chains to a few membered chains to rings and 2D and 3D extended networks. So these materials were mainly addressed theoretically in the past years. And when we started this research, only a few experimental studies on pentazolate were published. And in our first experiment, which was actually performed for the first time at ID27 of ESRF, we heated iron with nitrogen at pressure slightly above 1 megabar and got a compound FeN4 with its main structural feature, polymeric nitrogen chain running along one of the crystallographic direction here. Further, by changing the metal to more electropositive beryllium, we could get a similar tetranitride. And the following example comes from the work of Dominique Laniel, who showed that similar tetranitrides can be formed from magnesium and zinc at high pressure conditions. So although these 4 compounds, which I show you here, look quite similar, the chemistry of them is very different. And knowledge about the high quality, about the crystal structure and its refinement in the high quality X-ray diffraction dataset allows us to discuss the chemistry of these compounds. So here I magnify the fragment of the crystal structure containing this polymeric chain, and we see that there are 2 crystallographically independent nitrogen atoms here, and 1 atoms are coordinated by 3 neighbors forming planar triangular coordination, and 2 atoms are coordinated tetrahedrally with N2 and 2 distances much larger than 1 and 1 distances. And also these chains are quite heavily distorted out of plane. So the dihedral N1 and 1, 2 and 2 angle is about 35.8 degrees. Based on this crystallographic information, we could actually judge about the connectivity of nitrogen within the chains. And we interpreted it as a polytetrazine chain with 1 double and 3 single nitrogen bonds within this chain. If we now compare this with the magnesium example, we see that these chains are completely planar with 0 degrees dihedral angle. And there is only 1 symmetry-independent nitrogen atom. And all nitrogen-nitrogen distances are almost equal to each other. This allows us to say that we are dealing here with polyacetylene-like nitrogen chains with a full pi electron conjugation within these chains. And in case of beryllium compound, so beryllium is more electropositive than iron and less electropositive than magnesium. We have some intermediate situation where we have slightly distorted chains, and we interpret it as a partial electron delocalization within these chains. So the reason for such chain distortion comes from the polar covalent FeN bonds in FeN4 compounds. And in case of magnesium and zinc compounds, we are dealing with pure ionic compounds with no directional metal-nitrogen bonds, which allows the nitrogen chain to lock into the most stable configuration. So although all these 4 compounds are quite simple and they probably could be modeled in advance, sometimes high pressure chemistry in diamond-tunnel cells results in really complex compounds. For example, a series of metal and organic frameworks, which we synthesized with the transition metals, hafnium, tungsten, rhenium, and osmium, show that such frameworks form above 1 megabar, where we have channels in the crystal, in the structures, and these channels are filled with dinitrogen molecules. What's exciting about these materials that, for example, they have osmium to metal to nitrogen ratios, which one would never consider in the theoretical structure prediction. So we would never expect the composition of 5 to 34 with something about 78 atoms per unit cell, or 2 over 11 in the hafnium system. One of the successfully predicted systems was this structure of tungsten N8 times N2. It was predicted to exist in the hafnium nitrogen system. So from this couple of highlights, I move a little bit to our challenges, and would like to show you how our data really look like when we are moving to multi-megabar conditions. Of course, we always like when it looks like this, when we synthesize a pure phase and have no doubts in our structure solution. But sometimes when we make a multi-megabar experiment, we end up with a diffraction pattern like this. This is the diffraction pattern of iron oxide at 200 GPa, collected at the beamline, I think ID 27 with a beam size of 3 microns. And here we see mostly the diffraction from rhenium and a huge peak from diamond. And there are a few tiny peaks from iron oxide. However, when we bring such a sample to a beamline where we can focus the beam down to, for example, to 400 nanometers, this was the beamline ID 11 of ESRF, the same sample would reveal us much different features in the diffraction patterns. So we see nice lines of the new FeO phase, which was further solved and refined to quite well residual values. To show you some numbers, we can compare the structural refinements performed at the Microfocus beamlines and the standard dedicated high pressure beamlines. And we see that with the Microfocus beam, we can really locate the tiny grain of FeN4 in our sample and collect a very high quality data with better residual factors. And what's more important for the chemists is the high precision on the interatomic distances and angles, which allows us to discuss the chemistry of these compounds. So where we are moving to with the upgrade of ESRF and is the chemistry at terapascal conditions. So we know by now that we can create pressures close to 1 terapascal, and this is the figure from Leonid Dubrovinsky and Sayana Handarhaeva from their new paper, where they combined the toroidal toroidal diamond design and double stage diamond anvil design to reach the pressure of about 1 terapascal. And moreover, it was possible to heat the sample up to several hundred Kelvin at 1 terapascal. And what's even more interesting, it was possible to analyze such a reaction mixture which occurred after this laser heating. So I'm sure that ESRF-EBS and the submicron focusing capabilities of ID27 will provide many highlights in the next few years regarding the terapascal chemistry. Another wish from the high pressure chemistry community, as I can guess, is to study the chemistry of light elements. So far, we were really limited mainly to the studies of heavier elements at multi-megabar conditions. So here, for example, we see the diffraction of H3S at 224 GPa, which is already reaching our comfort zone for the high pressure experiments at third generation synchrotron facilities. And we would like to study all these new phenomena in hydrides of light elements, CH4, NH3, H2O, which would be important not only for high temperature, high pressure superconductivity, but also for determining the behavior of these elements and compounds in the extraterrestrial bodies, for example. With this, I would like to thank all the people who participated in this nitride research, and you for your attention.
Thank you, Maxime, for this nice talk. So is there any question? Camille Zubzek is asking a question. Camille?
Yes, thank you very much, Maxime. Very nice talk and a lot of interesting examples. My question is about the reliability of the atomic position determination at this very high pressure, I mean 200 GPa. And I absolutely believe in all the beautiful structures you shown in terms of the chemical bonding and in terms of the way the atoms are arranged in the unit cell. But do you believe that you can actually determine the bond length down to the third place and after the decimal point in angstroms in 2000 GPa? And did you try to compare, let's say, independently two different grains of the same phase from the same sample, just to check it out?
That's exactly what we are doing in order to make a proper like refinement of the intraatomic distances. You should analyze maybe 10 grains or so, and then take an average of them, because this gives you much higher reliability on your intraatomic distances. That's what so when we have access to, let's say, to multiple grains, we would usually do this kind of analysis when we are really discussing the tiny details of chemical bonding.
Okay, and the spread of the distances is not so very wide. So you actually believe that all of them are focused around the middle value.
Yes. So it depends from phase to phase. So it depends on what is the highest, what's the heaviest element, what is the lightest element in the systems. It depends on the size of the unit cell, but yeah, usually it's within 0.005 angstroms or so. If you have a high quality data set, so I have to say that it depends. So,
okay.
So your question has a lot of sense to it, and one have to discuss the proper way of doing this in the future, I think.
Sure. Thank you very much.
Another question? So I'll ask mine. For the case of osmium, with this complex stoichiometry and structure, in the sample, there were other stoichiometry probably, or was it the only stoichiometry? And so the other way to do it would be to have a nanograin, a very small grain of osmium in nitrogen, and to probe this very rich nitrogen sample. So do you see what I mean? Either you start with osmium and embed nitrogen, and you make a lot of stoichiometries because you don't have time for full synthesis, diffusion, and everything, or you start for very small grains embedded in nitrogen, and then you have a single grain. You have time to really synthesize your sample.
Yeah, this is the direction which actually we are thinking about. So usually when we have a big piece of osmium in the center of our diamond cell, and we usually have a phase distribution starting from osmium N2, for example, and to more nitrogen-rich phases towards the boundary of the osmium piece. And what you suggest is actually what we are also thinking about, to really start with the real big excess of nitrogen over osmium over all place, but we did not do this experiment. So we basically dealing with multi-phase sample too, but then we just picking up all the phases which are present in the sample afterwards.
Okay. So another question: what's the effect of stress to refine the structure? I mean,
so usually after the laser heating, we remove the stresses from our sample, so they recrystallize as very nice non-stress single crystals.
Okay, thank you. Okay, thank you. For me, the program is finishing, but you told that there was someone speaking after.
Yes.
So I have another program. So Rafaela, can you?
I confirm that this last talk was added. Probably you don't have the last version of the program.
Yes, right. I didn't have it. Okay.
Sorry, Paul.
Okay. So
yeah, there is a last talk from Andrei Aslanbukov from the University of Bayreuth.
Yes.
Okay, sorry. Okay. So
yes. Good afternoon, dear colleagues. Today I would like to present to you domain after finder program, the analysis of X-ray diffraction data from polycrystalline samples. And in the end of this talk, I would like to demonstrate to you how to use the program and run it on the real example. X-ray, single crystal X-ray diffraction is a powerful method for determination of crystal structures. Normally, it can be applied for single crystals not smaller than dozens, hundreds microns. But many materials are only available in the form of polycrystalline samples or as fine powders. But recent development of the synchrotrons provides X-ray beams with very high brilliance and small size that make it possible to apply single crystal X-ray diffraction to polycrystalline materials. Indeed, for samples which can be studied only by powder X-ray diffraction at home diffractometers with a big beam size, at synchrotrons with smaller beam, we can illuminate less crystallites, and as a result, see better well-defined single crystal diffraction spots. And the power of these methods was demonstrated in the case of laser heated diamond tunnel cells, where a lot of different exotic structures were solved. Now the crystallographic packages for single crystal data processing, such as Chrysalis Pro, are working well with single crystal data, single crystal X-ray diffraction data obtained from normal single crystals. But in the case of polycrystalline materials, where step scans contains diffractions from several crystallites, such programs are not able to find the unit cell to work in with. This situation is even more complicated in the case of high pressure studies in laser heated tunnel cells, where we have a lot of parasitic reflections from diamonds, pressure transmitting medium, and so on. So usually the typical procedure of data processing in the case of polycrystalline samples are following. So after peak hunting in programs such as Chrysalis Pro, we get a peak table which contains all coordinates of our reflections. Then in the case of high pressure data, it's possible to apply advanced filtering to remove diamond peaks. And then the most important, we need to perform manual search of groups of reflections in the reciprocal space belonging to the different single crystal domains. And only after such manual procedure, we can index all of these found several groups and perform integration and structure solution. So usually during the rotation of initial cloud of reflections in the reciprocal space, we try to find several rows of reflections in the same direction by eye. And once we find 3 lines, Chrysalis can index them and find other reflections belong to the same single crystal domain. But of course, such manual procedure can require a lot of time. And of course, we cannot manually find, for example, 100 domains. That's why we can miss something. But now this problem is the past. And we have a solution for this. And this is Duffy program, which I would like to present. So now, after peak hunting, we can just ask program to find n reflection groups, and program iteratively will do it. And after that, all found groups, all found groups can be indexed individually in Chrysalis. So the general idea. Of course, any 3D lattice is defined by 3 lattice vectors. But as I showed you before, usually we are looking for several rows of dots lined only in one direction. And this is enough for Chrysalis. So that's why the idea of algorithm is very simple. Let's just try to optimize the search of such rows in one direction. So the first stage of the algorithm is to select the best direction. It can be done by brute force search through all pairs of points. And for example, for given 6 points, we have different 15 vectors, but these 6 vectors corresponds to one direction. Then this is a good direction, which can be used in the second step. On the second step of the algorithm, we select the good rows of reflections, which boils down to select the proper distance between reflections in the chosen direction and kick out wrong reflections. And after second step, basically that's all. We found the reflections group belonging to the single crystal domain, and program can go to the next iteration and remove the found group from the consideration. So now let's look on the example. So a piece of yttrium and nitrogen was loaded in the diamond tunnel cell. Then cell was laser heated at PO2.2 beamline at DAISY. And as you can see, after laser heating, a novel phase crystallized. We collected single crystal X-ray diffraction data in plus minus 38 omega degree range. And peak hunting procedure in Chrysalis Pro found almost 70,000 reflections. Sun reflections here, those filtered by advanced filtering, so corresponds for diamond and other artifacts. And the Duffy program was asked to find 10 reflections groups belong to the distinct single crystal domains, and it took Duffy program a few minutes. And here you can see all found 10 groups marked by 10 different colors. After indexing and further integration of reflections group, for example, number 1, the crystal structure of reaction product yttrium 5 and 14 can be solved and refined down to around 4%. So summary, the Duffy program is designed for the quick search of subsets of reflections from individual single crystal domains in the whole set of single crystal X-ray diffraction data from polycrystalline samples. The algorithm finds these groups purely geometrically. That's why it neither requires a priori crystallographic information nor is limited by the number of phases or individual domains. The algorithm is applicable to datasets with many junk reflections, like in the example of laser heated diamond anvil cell. And it works very fast to enable online data processing during synchrotron experiments. Code was written by Matthias Landukov. The DAFI program will be available to free download from the internet as soon as the following article will be published. But already now, for any questions or suggestions concerning this program, you can ask me directly via email. I also would like to thank Dominique Lanier, who actively tested the program and gave a lot of useful hints for further improvements. And thanks for BMBF and DFG for financial support. And now we are going to the most interesting part of the talk. I would like to demonstrate to you how to use this program on the real example. I selected one example from my own data from recent beam time at ID15B at ESRF. So this is ytterbium and nitrogen in laser heated diamond tunnel cell at 50 GPa. So let me close the presentation, go to Chrysalis. So we collected single crystal X-ray diffraction data in plus minus 38 omega degree range. Maybe it's purely seen here. But after peak hunting, we found almost 23,000 reflections. And of course, by eye, it's very difficult to find reflections belonging to the single crystal, to the distinct single crystal domain. So as long as this data is from diamond anvil cell, firstly, we can apply advanced filtering to remove diamond reflections. And after that, we have 19,000 reflections. Then we can close this. So all reflections coordinates are written in big table in tabin file. So we have to copy this tabin file to initial data folder of DAFI program. So just copy here. Then we have to set up the program settings. It's very simple. It can be done in config file. Here we have several parameters, but actually, normally we have to change only 3 lines here. So the first one is name of your tabin file, name of your big table. In my case, this one. Here we should put number of groups we would like to find, for example, 10, and number of groups to find in one iteration. Let's also put 10 for higher speed. And that's all. We are ready to start the program. Just click to main exe file. And it started. So here you see information about current tabin file. So in the first group, we have 19,000 reflections, in which the program tried to find single crystal domains. So the second group is filtered diamond reflections. So now program performing first stage of the algorithm. So trying to look through several directions. Of course, the running time of program strongly depends on initial number of reflections. But I think in this case, it will take maybe around 1 minute or less. So yes, that's all. We are going to the second stage and find different groups. Okay, all groups found in 55 seconds. Then program overrides the initial tabin file, initial pick table. So we have to copy it again. Oops. Paste to our initial Chrysalis experimental folder. So yes, replace. Open the Chrysalis. Read this tabin file. Yes. And let's look at the reciprocal space. So now here we can see all found 10 groups, for example, group number 1. So these reflections indeed belong to one single crystal domain. We can try to index these reflections. Yeah, so this is orthorhombic space group. It's following unit cell parameters. And we can go through all of them. For example, group number 2. Can try to index again. Okay. So this is the same phase, the same orthorhombic phase with same lattice parameters. And we can go through all 10 groups. Let's go, for example, to group number 10. Index. And as you can see, this is another phase. It's monoclinic phase with another lattice parameters. So basically, that's all. You can index all of find groups and then perform integration and solve crystal structure, new crystal structures of your compounds. So that's all. Thank you for your attention.
Thank you, Andrei, for this impressive demonstration of this new program. Is there any question? Yes, Kamil Jubzek.
Yes, thank you very much, and congratulations. I guess it's a major step ahead for what we have in high pressure synthesis and analysis of the single crystal data. My question is about in your presentation, the second slide. I guess you shown the tiny crystallites, like okay. Exactly this one. So a beam size which is around 50 per 50 micron, and the other which is 2 per 2 micron. My question is, because you presented the example from ID15B, and I guess the beam size was not so very small at that case. But do you believe it's better to, because I guess you and also people who were collaborating with you, like Dominic, used this program for various experiments from various beamlines. It's better to have a larger beam for this situation, just to cover a higher number of crystallites, or with just such a tiny beam, are you not afraid that some of the crystallites are not constantly within the beam when you are rotating the cell? When you're rotating from -38 to 38, you can just have some of the crystallites passing through the beam during the full rotation, and then it limits severely the
So I would say that even beam with size of 2 by 2 micron, it's still quite big beam, and we catch thousands of crystallites, thousands. So I would say that this beams around 3 by 3 and lower is a perfect beam size for such data.
Okay, next question, Carsten Detlef.
Yes, could you please comment on the differences between your approach and the approaches of that are used in the metallurgy community, like 3D-XRD and HEDM, it's usually called in the US, that are used, for example, on ID15A?
So we use another approach. We let me show maybe another slide. So our algorithm works purely geometrically. So we have just initial set of reflections in the reciprocal space, and just to try to optimize our manual procedure to find such lines in the one direction. And that's why we don't need any information about the unit cell lattice parameters. We don't need any information about how many phases we have our data set. and so on. I think this is a main feature of this program.
Okay.
And as far as I know, so this 3D XRD programs like grain spotter and so on, we try to use them for analysis of our data from laser heated diamond tunnel cell. And in the case of presence of a lot of junk reflections from diamonds, these programs also were not able to find the single crystal domains. But in this case, we can solve this problem.
To the best of my knowledge, for grain spot and things like that, you have to have a fairly good idea of what the crystal structure is, what the unit cell parameters are for the program to identify the peaks for the indexing. How does your search algorithm scale? How does the computing time scale as function of the number of reflections that you have?
So it's n square by log n, search complexity.
Okay, thank you.
Okay, thank you. So we have to close the session now. Who is going to give some concluding words of?
I'm going to say a few words, Paul.
Okay. Olivier, okay.
It's the end of the day. We have this micro-symposium dedicated to high pressure program and science at the ESRF-EBS. Our goals with this micro-symposium was to present the characteristic of the new EBS source at ESRF and try to see how it represents opportunities for high pressure science. We try also to present the new beamlines that have been optimized for the EBS, like the beamline ID 27, the new user facility, in particular the high power laser facility, and new experimental upgrades that are available for high pressure science at ESRF, like new detector on an ID15, for example. And we try to highlight these new opportunities with the first result using EBS. Okay, so as you may see, the high pressure program at ESRF is very developed, and there is many beamlines that are producing high pressure science, and they are now almost all back in operation after the EBS upgrade. Okay, so we hope to have met the micro-symposium objectives and to stimulate your imagination and your creativity for future projects and collaboration here at ESRF. We remind you that the next deadline for proposal is the 1st of March, the next call, and naturally we remain at your disposal for any further information. We would like to really thank Eva for the administrative support, to the very efficient administrative support, sorry, and for the organization. Okay, we would like also to thank the ESRF user office for the technical support and all speakers and chairperson from the day. And we cannot conclude this symposium without evoking the memory of two dear friends of high pressure who passed away at the beginning of this year. It's with deep sorrow that we learn the death of two colleagues, the Professor Paul Macmillan from the University College London and Dr. François Baudelet from the Synchrotron Soleil. They both made profound contribution to the high pressure science in general and to the ESRF high pressure program in particular, and they will be deeply missed. So it's on these very sad news that we are going to conclude this micro symposium. Again, I would like to thank all of you for your contribution and your attention.
And we hope to see you very soon in person at ESRF for a beautiful experiment or in the next high pressure workshop. So have a nice evening and goodbye.